الله الرحمن الرحيم. Assalamu alaikum wa rahmatullahi wa barakatuh. After spending all this time developing process models for simple processes, I think we have reached the conclusion that we cannot always implement this technique due to different difficulties that may be encountered during the modeling process. Some of these difficulties, probably the information needed for the development of the model are missing, or the model is complex enough that hinders the smooth development of it. And sometimes developing such models needs a lot of effort and time. So there is an alternative approach in which we use empirical data collected from the process itself or from a simulated version of the process to approximate the model of the process. Now, this approach has a major advantage is that it is less costly and it needs less effort. However, there is a main disadvantage in this approach. The disadvantage is that the model that will be created using this method is valid only for the operating conditions at which the data was collected. So that means if we use the model at different operating conditions, it will not be valid. The approach in this technique is useful for you, especially knowing that the method that will be used for modeling the process in the project of this course, as well as for the FYP, you will be implementing this method, and for that reason you need to pay good attention for this technique and make sure that you understand it very well. Developing an empirical model needs some precautions. So if you decided to use the input-output data collected from the real process or from the simulator, you need to take the following precautions during and after collecting the data. So the first one, make sure that the process was at steady state before the data collection started. The second one, you need to make sure also that the first point in the data collected is the same as the steady state value that was under the process with step number one. The third precaution is that you need to make sure that the dynamics of the process dominates the process noise. The fourth precaution, you need to make sure that the disturbances affecting the process were quiet during the data collection. And the last precaution, you need to make sure that the final fit for the model visually approximate the data plot. Now, I've just mentioned the titles of these precautions, and we will come to each one of these in the next slides. So the most important and the first precaution you need to take care of is whether the process was at steady state or not when you started collecting the data. This is a very important step, and depending on it will decide whether your data is feasible or not. Let me show you this with some schematics to understand the exact meaning of this point. Let us assume that you have an input for the process at a certain value. Let's say that you have this input at a certain value, and for some reason there was a step at this time, stayed for some period of time, and then went back here and then continued. Due to these changes in the process, there was also changes in the output. So the output was some value here, and then at this point where the first step has been introduced, at this point the process started to react, and at this point, at the next step, the process started to come back to this place, and it went to a steady state. Actually, this is the steady state here at this point. So you came here, let me select another color. You came here at this point and you decided to collect the data. So actually, if we reflect this, here the input is silent, but if you go up, the output is here. It is not really at steady state, which is this point. And from here you decided to make a step change, so you went up and then you made your step. So what you will be having is another response for the process, and you will reach another steady state. Okay, so you have started collecting the data while the process is still underway, going for the steady state. It did not reach the steady state, and now this collected data is not correct. The reason for that is that the starting point of collecting the data was not at the steady state. This is the steady state while you have started here. So actually what you should have done is that you should have watched the output and wait for it until it reaches the steady state, probably at this point. And then at this point, you introduce your step. So you should have done something like this. Here, from here, go up to your step. And this is what you need to do. Make sure to start the collection of the data when the process have settled down and you are working at the steady state conditions. After collecting the data, the other thing you need to make sure is that the first point in your data set should represent the steady state. So let's say that you have collected x and y data, or u of t, this is t, u of t, and y of t. So at t0, you have collected your u of 3.5, and y was 18.6. And then at the time step 0.1, this was 3.6, and this was 19.2. And then so on, you went collecting the different data set, and you have reached some point. So you keep continuing collecting the data. So this steps means at the time of zero means the starting collecting the data. At this point, make sure that this u and this y is the steady state conditions of the process at the beginning of collecting the data. If it is the case, leave the data as it is. Otherwise, you need to edit your file, remove these 2 points, and put the actual steady state. Probably the steady state was 3.55 and the y was 18.75. So edit them and put them manually in the data file. The third precaution that you need to consider when you collect the data is the noise in the process variable. Now we know that when we collect the data, we will not get smooth data because of the noise available in the process, and these noises are introduced in the process signals due to different reasons. Some of them are due to the other electrical devices surrounding the sensor. like motors or compressors or generators. Even normal lights will generate noise in the data. So we need to consider this noise very carefully, and we need to work with it in a way that the dynamics of the process should dominate this noise. And what we mean by dominate is that the dynamics of the process should be large enough to hide the effect of the noise. In dealing with signals, it is always good to define what's called the signal to noise ratio, or SNR. And this is a ratio, a number, dimensionless number, which measures the level of comparison between the signal to the level of noise surrounding it. The SNR is defined as the data mean divided by the data standard deviation. So if we have a data like this, a noisy data, we need to define the SNR. So we take the mean and the standard deviation, we divide them, and we get the SNR. So this is the first thing we need to do. And then we need also to define what's called the noise band. As you can see here, the signal, this signal is supposed to be at steady state, but still it is noisy. So we defined an upper limit and a lower limit. The signal in between is called the noise band. And this is defined as 3 times the standard deviation of the random error surrounding it. So we take the standard deviation, multiply it by 3, and this will be the noise band. So from the top it is 3 sigma, and from below it is 3 sigma. So the total will be 6 sigma. Okay, this is called the noise band. And of course the sigma, when I say sigma, sigma is the standard deviation as we know it from statistics. You need to know the mean in order to calculate the standard deviation. So now you know two things. You know the SNR, signal to noise ratio, and you know the noise band. So using these two pieces of information, you need to make sure that the output of the controller is strong enough to force the output of the process at least 10 times this noise band. So the value of this noise band, multiply it by 10, then the output in the Y, the process output, should be 10 times as much as this noise band. Or you can say that the SNR should be greater than 10. So whatever definition you use, this assures that the process dynamics is much more than the process noise, and of course this will make the signal or the excitation of the process is clearer to notice and use in the calculations. Let me show you a few examples to demonstrate the meaning by this point. Now here we have few examples of data collected from the process. As you can see in this example, the signal is very clear and it is suitable for analysis. This is the output signal. This signal was collected under a signal to noise ratio of 10. Okay, so this is correct. Now reducing the signal to noise ratio to 2, you can see now the noise started to be introduced and clear in the response, and of course this is not usable data. Even if you go lower in the SNR, the noise will be much larger than the actual signal of the process. With a very small SNR, the noise is so large that it hides the identity of the original signal. If you look at this, you cannot decide whether this is the same as this or not. Okay, so this is the effect of the signal to noise ratio. Now, when you collect the data, make sure that you have an SNR of more than 10. Let's have a few more examples in the next slide. This is the data collected from the two tanks connected to each other with a noise band which is 6 sigma of 0.24. The input was from 50 to 70, and the the flow rate of the exit stream jumped from 2 to 4. You can see that the signal is clear, although there is noise, but the signal is very clear for analysis. This was using an SNR of 100, which is of course much greater than 10, and that's why the signal was very clear. Now, reducing the SNR to 20, which is still greater than 10, we can still see the signal geometry, and this is still usable. Why? Because the SNR is more than 20. But when we reduce the SNR to below 10, this is what we will collect. And as you can see, the signal here is unclear at all. We cannot use it, although this is the same test. But of course, here I've used a smaller test from 50 to 55. But you can see that the noise is much larger than the change in the signal, and it has hidden the details of the signal. So to summarize, for this point, you need to make sure that the SNR is greater than 10. Now, how can you make sure this? You need, once you collect your data, you measure the mean and the standard deviation, divide them, get the standard, get the SNR, and then decide about whether the data is usable or not. Usable if the SNR is greater than 10, not usable if the SNR is less than 10. The next precaution to take care of is whether the disturbances were quiet during doing the dynamic test for collecting the data. Now, let me show you an example, probably the best way to explain this through an example. This is an example of a CSTR where we have two components added to react, and then we have component C exiting. So here we have, of course, it is well mixed, and we are trying to collect data from the flow rate of component A. Let's say that you want to collect data from here. So there is a flow sensor, flow transmitter. This is the input, where you have a valve here. And the output is this one. You are collecting the temperature or the concentration. Let's say the temperature transmitter of the exit stream. So this is your input, and this is your output. Okay, so when you started the test, everything was at steady state. All the 3 points were satisfied, but you didn't notice the stream B. Stream B is regarded as a disturbance. Its temperature, its flow rate, and its concentration, probably, all of these are disturbances. So if for any reason any one of these variables change during doing the test, then the dynamics caused by the change of the disturbance will affect the dynamics that you are collecting, the dynamics of stream C temperature. This is because the disturbance B was not silent. What we mean by silent or quiet is that it shouldn't change. Silent means it keeps the same value. So that's what we mean by making sure that the disturbances were quiet during doing the dynamic test. Now, if you noticed any disturbance change during doing the test, then the collected data will not be good, and it is corrupted, and you need to rerun the test. The last thing that you need to do to make sure that the data collected are of good quality Now, what you need to do is to compare the actual data. This is, let's say this is the actual data for the output, and you have modeled this data using some model, and you came up with something like this. This is the model. So this is the model, and the red line is the actual data. Okay. So as you can see, these two lines do not overlap, and that means that the model that you have developed is not explaining the dynamics of the process properly. So this also means that the data that you have collected is not appropriate, and probably you need to do the analysis. This is one reason. The other thing is that if the model is not suitable, this phenomena may happen, and then probably you need to change the modeling approach, as we will see in the next few slides. So these are the 5 important factors that you need to take care of when collecting data, and if all these were satisfied, the data collected will be of good quality and represent the actual nature of the process, and can be used for further modeling and analysis. After collecting the data, the input-output data, so actually what you will have is something like this. You have time, you have input, and you have output. Now, time is not really important. All what we need is the time step. But what is important is the input and the output. So we will start modeling the data using simple models. We will start by the most used models, which are the first and second order transfer function models. And the fit for the data can be obtained by using what's called a process reaction curve. Basically, the process reaction curve is simply introducing a step change in the input and collecting the output. This is called the reaction curve, which represents the dynamics of the process. So this reaction curve can be approximated with a first or second order model. Considering the first order model, this is the form of the transfer function in the Laplace domain, and this is its form in the time domain. Remember that k times m, m is the size of the input, m is this is m, and k is the steady state gain of the process. K times m together will represent the final steady state of the y. Okay, tau is the time constant for the process, which represents the speed of response. Let's see how can we implement this on actual data. Considering a first order model, which is something like this. This is the response of a first order model, y and t. Okay. Now we need to calculate the values of tau and k. Now for tau, the time constant of the process, what we need to do is to find the derivative of the curve at time is equal to 0. So what I need to do is to take the slope of this line at time is equal to 0. Okay, at this time. So what I'm intending to do is to differentiate the y over km at time is equal to 0. Differentiating this and substituting 0 will give me 1 over tau. So that means that if I want to get the value of tau, all what I need to do is to differentiate the reaction curve at time is equal to 0. And if I consider the derivative of the y, not y over km, then the output will be km over tau. Now this is the time constant. The gain of the process can be calculated from its definition. The gain is defined as the change in the output divided by the change in the input. And we know that the input is a step change of size m, so its change is m, so that means that the k is delta y over m. Once we calculate the tau and the k, that means that we have found the parameters of the first order model, and we can substitute in the transfer function. So the time constant can be also calculated using another approach. The time constant can be defined as the time needed for the output to reach 63.2% of its final steady state value. Now probably you will be asking why 63.2. Okay, to know why is it 63.2, we need to do some analysis. So if we go for our process model, you remember the process model, the y of t is equal to km 1 e to the minus t over tau. And if we bring this km to the other side, then what we need to do is to take the value of time is equal to tau. What will be the value of y? So if I substitute here for t, tau, and here, tau. So you can see now if you substitute tau, this will be e to the minus 1, and e to the minus 1 is 0.368. So 1 minus 0.368 is 0.632. And this is the ratio, which when you convert it to percentage, it will be 63.2. Graphically, this also can be demonstrated. The graph here represents the output of the process, the exponential graph. And if you take the tangent to the graph at time is equal to 0, you will have this line. If you keep extending the line until it crosses the steady state value, and then this point of intersection you reflect it down, what you will get is the tau. This is the tau. Now this distance over this distance is 63.2%. Okay, hopefully now you understand what is the meaning of 63.2. Now we don't need to do this. What we need to do is to make the tangent, and then when it crosses the steady state, we reflect it to the x-axis. This will be the value of tau, and this will represent the time needed for the process output to reach 63.2% of its steady state value. To complete the description of the first order process, we need also to introduce the time delay. Now the time delay is important because most of the process variables are delayed when an excitation in the input happens. So now you have three parameters. You have the process gain, you have the time constant, and you have this theta, the time delay. And that's why this is called the first order plus time delay model, for short FOPTD. Okay. Now I will show you how to calculate the theta later on. We have calculated k and tau so far, but we need to also consider the theta. The first order response has some properties. The first thing is that the response attains 63.2% of its final state value at a time of tau plus theta. Remember that we have theta here, that's why we have added it to the tau. And then the line, the tangent at time is equal to 0 intersects with the steady state value at t is equal to plus tau plus theta. Also, if you leave the process for 5 taus, it will reach its steady state value. So that means that the settling time of the process Ts is equal to 5 tau plus the delay time. These are just properties for the first order plus dead time model that we need to put in mind when we do the modeling. In practice, the data collected will not be smooth. You will be having probably data like the one shown here. You can see these noisy points here. And when we try to implement a first order model to this data, of course you know that we have to find three things. We need to find the k, which can be calculated actually easily. However, the tau and theta sometimes are challenging to find, because let's say a graph like this, the theta is the time needed for the process to start changing. So if the change in the input happened at this point, at point 0, the process needed some time to start moving up. But this does not happen like the way we write in books. The data is noisy, and that's why you see something like this. So how can we find this theta? And also, how can we find the tau, which is found by making the slope of the curve at time is equal to 0? In that case, we probably need to do the tangent to the curve at the inflection point. And you know from mathematics, the inflection point is the point at which the curve changes the sign of the second derivative. Or you can see here that the curve is going up here, going up, but after the inflection point, it is going down. Okay, so it is increasing. The rate is increasing here, but now the rate is reducing. So it is sometimes challenging to find the theta and tau from experimental data. Now about methods of finding the parameters of a first order plus dead time model. The first method, we will call it the slope intercept method or the reaction curve method. In this method, we need to draw the slope through the inflection point of the process, like the one in the previous slide, and then we can find the tau and theta from the graph. This is one way. The other way is to find tau by the time that the process takes 63.2% of its final value at the settling time. So we will implement these both methods and see how can we do this on real data. This is an actual data, and I will leave you a copy of the data in the Moodle so that you can practice the method on it. We want to have a first order blood dead time model for this process. So we need to find K, tau, and theta. This is the curve for the input. The input has changed suddenly at this time from a value of almost 50 to a value of 70. And because of this change, the process reacted. So it was at this steady state point, and then it went up to another steady state value in an exponential manner, not necessarily first order, but we will be approximating it with a first order model. So the first thing we need to find is the dead time. Now, as I said, the dead time is the time needed for the process to react. So it is the distance from the starting point of the, once you know the theta, so now we know the theta, we can find how much is it. So it's the difference between these two. Based on my calculation, it is 0.5 seconds. Next, we find the tau. We will make a slope from this point, a tangent from this point up, and a line from the steady state. They will cross at this point. Then we will project a line down and get the value of the time here. The difference between this time and this time will be the tau. So here it is 18.2 minus 16, which is equal to 2.2 seconds. Now we've got the theta and we've got the tau. The last thing is the k. Now k, we know that the k is defined as the change in the output divided by the change in the input. For the input, it changed from 50 to 70. So this is m. This is the change that we are looking for. It is 70 minus 50. For the output was 1.9 and it went up and reached another value of 4. So the difference between the two is 4 minus 1.9. This will make it 2.1 divided by 20, which is 0.105, and then the unit. The unit is very, very, very important for K. See, I've said very 3 times. If you don't put a unit for the K, it means that the quantity is unknown and I will regard it as wrong. Make sure to put the unit for the K. Now the unit of K is the unit of the output divided by the unit of the input. So the unit of the output, this unit of this variable divided by the unit of this variable. Now I have collected this data for the level. The output is the level, and the input was the percentage opening of the valve. So that's why the unit is meter per percentage. Now after calculating the K, I have all the parameters for the model ready, the theta, the tau, and the K, so I can substitute in the general form of the model to get its transfer function. GOS, the transfer function of the process. Remember, the transfer function of the process is defined as Y of S divided by U of S, the output divided by the input, is equal to 0.1045 e to the minus 0.5 s divided by 2.2 s plus 1. And this completes the modeling using this method, the slope-intercept method for a first-order process. Now, sometimes it is difficult to calculate the tau from the curve because it is difficult to decide about the point of starting the slope or finding the point of inflection of the curve. And that's why we need to use another method in that case. The method is called the SNK method, which is related to those two scientists, Sundari-san and Krishnaswamy. These two, the method of these two guys depends on 2 times, T1 and T2. You need to find T1 and T2 from the graph. And based on the value of the T1 and T2, you calculate the tau, the theta, and the tau. Now, the T1 and the T2 can be calculated from 35.3% response time and the 85.3% response time. So that means if you have a response for the Y, let's say something like this, and the data started from this point. So taking all this distance, this is 100. If we take 35.3%, it is this distance. So if I calculate up to this point, this will be T1. And if I calculate 85.3%, this point, this will be T2. I will show you this later more clearer in the actual data. And then once you calculate T1 and T2, then you can calculate the theta and the tau. So these values of theta and tau will minimize the difference between the measured response and the model based on the correlation of many data sets, which means that these numbers, they got them from doing some optimization studies on many data sets, and they came up with these numbers. It is not important for us now to know how did they get it, but we need to know how to apply these two correlations. So let's go back to our first example. Now we will remodel the process using a first order plus dead time, but now we will use the SNK method instead of the reaction curve method. So again, we will decide the point at which the input started. This is T node. T node, it is the point at which the input started. And then we will calculate the T1 and T2. So to calculate the T1 and T2, remember that T1 is the value of Y at 35.3% of its value. So that means we need to apply this equation, which says that Y at a certain percentage is equal to the first steady state plus the percentage that we need for T1 and T2 divided by 100 times the second steady state minus the first steady state. Now the first steady state is this, the second steady state is this. So these are the Y1 and Y2 bars. So Y1 bar and Y2 bar. And once we have these, this is Y1 bar, Y2 bar, and we know the percentage, we can calculate how much Y at this value. So calculating T1, it is Y at 35.3. So I just divide 35.3 over 100 and I apply the equation. Y1, this value is 1.95, Y2 is 4, and then I can calculate the Y at T1. So once I have this value, I can find it on the vertical axis. It is this point, and then I will draw this line until it crosses the reaction curve, and then, or the output variable, then I will project it down until I reach the value of the T1. So this will be T1. This is not accurate. Now I will show you a more accurate drawing. The second one is the Y at T2. Remember, is Y T2 is the time at 85.3. So I will apply the same equation, but now I will use 0.853. This will give me 3.7, and then this is the 3.7, and then drawing this horizontal line until it crosses the Y, and then I can go down. This is T1 and this is T2. So this is T2, but the value, the actual value of T1 can be calculated from T node. Actually, it is this, the T1, and it is this, the T2. So T1 minus T0 is T1, and we shouldn't call it T1, probably we'll call it T1 prime, just to make it easier. So this is the T node minus the T1 prime. This will give me T1. And similarly, the T2 is equal to, sorry, it is the other way around. This is the T1 prime minus T node. And the T2, it is the T2 prime minus the T node. Okay, so it is 19 minus 15.5. 19 is this point, 15.5 is this point, so the difference between the two. Similarly here, the 16.6 is this point, and the 15.5 is the same as T node. Now we have found T1 and T2. We'll use the previous correlations for theta and tau. We just substitute T1 and T2, and then we get the theta and tau. K will be the same as the value calculated before. This method will not change the value of K, and then we can substitute in the general form of the model to get the value of the approximation for the model. Now, if you compare this to the previous model, it is very close to it. However, it is not really the same. Now, why it is not the same? Simply because we are using different methods for approximating these models. A third approach can be used for modeling the process is using software. We can use some dedicated software for modeling the output-input dataset. One of the softwares that we used to use is called the Loop Pro. And we're using this software. I can let the software calculate for me the model. Unfortunately, the Loop Pro license has expired, and we cannot use it now. We are trying to reinitiate the process of licensing. Once it is ready, I will demonstrate for you how can we get the model using this software. But in the meantime, the software can be used, and we get the model. The model will be given. So, for example, this is the gain, this is the time constant, and this is the dead time. And the accuracy of the model, this is the R squared and the sum of squared errors. I did the modeling using the Loop Pro, and I got the model that you see here. This is the model that I got with the design tool in Loop Pro. This is the model using the reaction curve or the slope and tangent method, and this is the model using the SNK, and this is the one using the design tool. Now you can see that the K, for example, is 0.105 in both models because the calculation is the same. However, here it is a little bit away, 0.1036. The dead time is 0.5 here, while it is 0.415 here, and it is 0.583 here. And the time constant 2.2 here, 1.6 in the SNK, and 1.51 using the software. Now, which one is more reliable? Of course, we can easily say that the design tool is the best approach because it uses optimization and mathematical techniques to come up with the values, and they are not related to the human limitations that were used in the slope and tangent method and the SNK. We use our eyes to decide about the slopes and values from the graph. So the final results will not be as reliable as the software results.
Another type of processes which is very common in the process industry, which is called the integrating process. An integrating process is a process at which mass or energy accumulates with time. And this happens usually for both mass as well as energy systems. For example, I'll give you a few of these examples for the mass systems and for the energy systems. For the mass systems, the example of a liquid level control, for example. Here you have two streams, one inlet and one outlet. So if one of these streams has been manipulated, keeping the other stream fixed, then mass will be either accumulating positively or negatively, and this will create an integrating system. Another example is the gas pressure control. Here we have a tank in which gas is being injected, and there is another stream for exiting the gas. So manipulating one of these streams will create, while keeping the other stream fixed, will create an integrating process. For the energy systems, the temperature control is a good example. Here, manipulating flow of heat in one of the streams and keeping other heat flows constant will create an accumulation of energy. Another example is the speed control, where the force or torque applied to a mass is manipulated and all other forces or torques kept constant. So coming back to the simple example of having a liquid tank, here we have a liquid tank with an inlet flow into the tank, and there is an exit from the tank. There is a pump here, and since there is a pump, this means that this flow rate is fixed, and hence this will create an accumulation of mass and consequently an integrating system. The other stream here is a disturbance. So in this case, the model of this process will be an unstable process. So that means if we draw the output y, which is the level here, with time, it will be going either up or down depending on the way we manipulate these streams. And in that case also, there will be no steady state. So the system will keep going up or down. And we cannot apply the technique that we have used previously for modeling an integrating process in this case. The modeling of such a system involves calculating what's called the integrator gain. So notice the star here, which means that this is not the steady state gain. It is called an integrator gain, and this is defined as the ratio of the process gain to the process time constant. So it is all in one, both parameters in one parameter, and the units will be the units of the process variable divided by the units of the control output times time. So the integration process, the process in this case has no steady state gain actually, but it has a gain that is calculated in this way by finding the slope of the curve between two particular time points. Let's have an example and see how can we model an integrating process. Now, to model an integrating process, instead of one step as we did in the previous case of first order system, we need to do two consecutive steps in the input, and then we calculate the slope of the output at the point of change of the slope. So let's have an example of such a case. Here we have the input. This is the input. So it started at 70, and at a certain point we did a step. This is a negative step, and then after some time we did another step, and then we kept it for some time, and then back to the original point of 70. This is the way we do the change, the step changes in the case of integrating process. Now you can notice also that the output, this is the output, at this point it started changing with a constant slope. This is an integrating process, and when we did the other step here at this particular point, the curve started changing slope. So see this side, let me show the pen. Okay, so you can see that this is a line of a certain slope, and this line has another slope, two different slopes and they cut somewhere here. Okay, see, although we did the step here, the change in slope happened here. So the difference between the two will be the dead time. So how to model the process in this case? Okay, so first of all, you need to know the values of the inputs changes, and this is the model that you will be modeling. This is the model that you will be using. It has two parameters, the integrator gain and the dead time. So first we need to calculate the integrator gain. Here we take the second step and measure the value of the change in the input. So this is from 60 to 50. This will be 10%. And then we go up. From the point of start of the second step, we decide about the location. So this is the location of the first point. And then we notice the change in the slope. As I said, this line has different slope than this line. So at certain point, this point, the line started changing slope. The difference between the two will be the dead time. Then we calculate the slope of the next segment. So this segment, we calculate the slope as we do usually. We take the difference in y divided by the difference in time. So this is this has the units of the process variable, and this has the units of time. And we calculate the slope. So this is the slope, and then we divide this by the change in u that we have just calculated. So this is this, and from here we calculate the slope. The ratio of the two, so delta I is this distance, and delta t is this distance, divided by delta u is this distance, and the result will be the integrator gain, which has the unit of the process variable over time divided by the controller output or the input. So now we can write the equation by substituting the value of k and the value of theta in it. So this will give us this model. This is the model of the integrator. Notice that there is no time constant here because we have merged both the gain and the time constant in one, which is the integrator time constant. Next, we consider higher order processes, starting with the second order process. The technique is basically similar to the first order process, in which we do a step in the input and monitor the output, and from the output and input we calculate the model parameters. However, the problem here, or the difference here, is that the second order model will have different dynamics as we saw previously, depending on the values of the time constants or the zeta parameter. So here in the second order model we have two time constants, and based on these two time constants, the values of these two time constants, we will have different shapes for the dynamics. The figure that we'll show in the next slide will give you different shapes for different ratios of tau 2 to tau 1. And by the way, these tau 2 and tau 1, the highest value of both is called the dominant time constant. So if tau 1 is larger than tau 2, tau 1 is the dominant. Otherwise, it is tau 2. Now, this is the curve showing the dynamics of a second order process for different values of time constant ratios. Starting with the case of tau 2 over tau 1 is equal to 0, which means the value of tau 2 is very small compared to tau 1. or tau 2 is equal to 0. This is the case exactly similar to the first order system, where we have only one time constant. And as the tau 2 increases in value, then we see the shape becomes more concave at the beginning. See that at the beginning it is not starting strictly like the first case. There is some inclination, slow response at the beginning. And then as we increase the tau 2 more, the critical case, the critical damped case where the two constants are equal, you have the limiting shape of the S shape for the second order time, the second order model. Now, one of the methods to model a second order process is called the Smith method. Here, the assumed form of the model is this, where we have 4 parameters: the process gain, the dead time, the time constant, and the zeta, the damping factor. So how to use the Smith method? Well, actually here we need to find 2 times, T20 and T60, from the step response data, and from these values we use figures 7.7 in your textbook to find the value of zeta and also to find the value of tau. Once we have found the values of tau and zeta, we can calculate the time constants tau 1 and tau 2 from their values using these two equations. This is figure 7.7 from your textbook, and you can see that the x-axis is the ratio of T20 to T60, which we have calculated from the graph. I will show you next how to calculate these two. Once we have these, so we have the value in the x-axis. Now, to find the, let's say you've come up with 0.4, then you extend it, and once you reach the intersection with this curve, so you can get the value of T20 over tau, and then extend it more until you cross the other graph, and then from there you can get the value of zeta. So now you have the value of zeta and you have the value of tau. So this is an example where we have at 0.5 the ratio at 0.5, and then we found the T20 over tau, and also we found the zeta. These are the same figures but separated, just in case you want more clearer forms of the graphs. You can use these graphs, but the idea is the same. You just extend a vertical line and see with the value of the y-axis. Similarly here, vertical line, and see the zeta value. Okay, so this is the same example we used before to model a first order process, but now we will use it to approximate a second order process. Now, when should we use a first order and when should you use a second order? Actually, we always prefer to use a simpler model, a first order. However, if the model has some form of second order response, like for example here you can see at the beginning the increase in the y is not sudden like the first order. So this is an indication of an S-shaped model, which means that it is higher order. So coming to the model we have the k, theta, tau, and zeta. So k is calculated the same way we did for the case of a first order model. Even the theta has the same way. So the only thing is the calculation of the tau and zeta. So let's start from the step change. The step happened at 15.5, and then at this point we calculate the T20. Now the T20 is calculated similar to the way we calculated T1 and T2 in the SNK method. Here we use the, let me show the pen again. So we use the y bar 1, and then we use the y bar 2, y bar 1, so this is plus, times 0.2. Why? Because we are taking T20. 20 is 0.2 as a fraction. So this gives you the value of the y at T20. Once you find it, here it is 2.36. So I come to the y-axis, I pinpoint the 2.36, then extend a horizontal line until it touches the graph of the process, and then I bring it down. Next, I will calculate the y at T60 the same way. This is y bar 1, this is y bar 2, and now I multiply by 0.6. So the same thing, then I have these 2 points, then I will extend down to calculate the T20. Remember to subtract from the T0. So T20 will be the 16.5, which is this point, minus the 15.5, which is this point. It is the distance between the two. Similarly, for the T60, I need to subtract this point from this point. So 17.7 minus 15.5. I found the T60 and the T20. Now I go back to the equations of the Smith method to calculate the values of tau and zeta. So to do this, first I need to use the graph. To use the graph, I calculate the ratio T20 over 60. It is 0.45, and then from the graph I can get the values of tau and zeta. From figure 7.7 I can get T60 over tau as 1.7 and zeta as 0.75. Now to calculate tau, I know T60 is 2.2. So from this I can calculate the tau. I have now tau and zeta, so I completed the evaluation of the 4 model parameters. Then I can just substitute here. But if I want to put it in the form of tau1 and tau2, then I will use the equations to do that. So this is the value of the tau, and then this is the final shape of the second order model, where we have the process gain, the dead time or the time delay, and then the tau squared, and then 2 times tau times zeta. This is 2 times tau times zeta. If you have higher order dynamics, you suspect that your model is higher than second or even second, you can use another method which is called the Latzell's method. In the Latzell's method, we approximate higher order transfer functions of this form: k over tau s plus 1 to the power n. Well, we said we call it tau L just to differentiate it from the other time constant. Tau L here represents Latzell, but it is actually tau. So tau s plus 1 to the power n, where n can be any integer, any positive integer. Now tau L, of course, k here is calculated the same way we did with the first order and the second order. It's delta y over delta u. And the only thing is to calculate the tau L and the n. Now the tau L is calculated as alpha 10 T10 plus alpha 50 T50 plus alpha 90 T90. Now how can we get the values of these alphas and t's? The t values are calculated the same way we did with the Smith method, where we calculated the T20 and the T60. Here we calculate the T50, T10, T50, and T90. And then we calculate a parameter called mu, which is T10 over T90. So now we have T10, T50, T90, and mu. Okay? Then we use the table in the next slide to evaluate the tau and n. So once we have the mu and the value of the this value has been calculated by the T10 and T90. We come to this table. This is the mu. So for example, if we calculated mu between this number and this number, we approximate by rounding, so we either take this or this. So for example, if it is 0.210, then we take this line. The n value is 3, and then the alpha 10 is 0.9067, the alpha 50 is 0.374, and the alpha 90 is 0.188. So now we have the n already found. The tau L, as we said, is alpha 10 times T10 plus alpha 50 times T50 plus alpha 90 times T90. We have the values of all these, the times and the alphas, so we can calculate the value of the tau. So this is a very simple method, but you still need to have this table in front of you in order to use it, and you can approximate any higher order. See, the order can go up to 50 to 20, but just to let you know that in process control we don't prefer to go for orders greater than 3, because this simply means that the process is very complicated, and then this will cause us a lot of problems when you come to the control system design. So we always try to approximate processes using first, second, or maximum third order. So this completes the chapter for the empirical modeling using process data. As I said at the beginning of the chapter, we can use the techniques presented in this chapter to come up with approximated models for actual processes that we can access their actual data, or for simulated processes using process simulators. And then we can design or assume a model first, second, third, and then use the techniques to come up with this model.